So here we have a relative minimum. Because we go from increasing to decreasing here, the graph must look something like this. That's a relative maximum. And then because we go from decreasing to increasing here, it's a relative minimum. And if I look at the graph, I do see a relative minimum here. Granted, the little drawing that I drew doesn't look anything like that, but it is a relative minimum. This one is a relative maximum. This one is a relative minimum. Okay? Now, there was no interval specified, like they didn't say from -5 to +5. So we're going to infinity and negative infinity in our intervals. Usually with trig functions, they'll say from 0 to pi or something like that. So then you won't have infinity there. And the reason they do that is because obviously the trig function cycles. It repeats the same stuff over and over. So then our answer needs to be, we have relative minimum at, no. We're looking for the relative extrema. So this is asking me for a relative extrema. That means I need an ordered pair. If it was asking me for the intervals on which the function is increasing or decreasing, then you're going to include the intervals. So to answer this particular problem, we're going to find the relative minimum or minima, and then the relative maximum or relative maxima at, okay? So we need ordered pairs. We know that we have a minimum here, and we have a minimum here, so I'm going to have two ordered pairs. And then I'm going to have one relative maximum, so an ordered pair here. Now the x-coordinate that gives me that relative minimum or relative maximum is the critical number that I found. So I have -2 comma something, +2 comma something, and then, oops, yeah, that's right. And then my minimum or my maximum occurs at 0 comma something. Okay, so then we just plug these values into our function. It's probably going to be pretty easy to plug 0 in. I get -4 to the 2/3 power, and again I can square first and then cube root, or I can cube root first and then square. Square first. So I got -4 squared is +16, and then the cube root of +16. I have that, right? Is there a perfect cube that's in 16 though? 8. So the cube root of 8 is 2. Cube roots of 2. So you could write your answer like that. Okay, the other one, we have -2 squared would be 4. 4 minus 4 is 0. 0 to the 2/3 is 0. And then 2 squared, we're going to get the same result. 4 minus 4 is 0 to the 2/3 is 0. So those two were easy. This one was a little tough. But no big deal. Just be aware of the directions, what they're asking for. Again, they're asking for these ordered pairs here. All right, once again, I give you the graph for this function. We want to find the relative extrema of this guy. We want to talk our way through it, or you want to just try that here? Just try it? Okay, we'll wind up talking our way through it anyway, but go ahead. Right off the bat, before you do anything, take a look at the function itself and see if you can pick out any critical numbers before you do an analysis of the derivative. Do we have any critical numbers? 0. Because of the division by 0 right there, we have a situation that we need to address. I plug 0 in the bottom and I get 0. I have division by 0. The question is, what's in the top? I get 0 plus 1, which is 1. So I have 1 divided by 0, which tells me that I have a vertical asymptote at x equals 0. So x equals 0 is a critical number. Now I'm pretty positive that I'm going to have at least one more critical number, and actually, obviously I do since I have the graph sitting here. But because of this numerator, I'm guessing this thing turns around or something like that. I'm trying to imagine this thing without seeing the graph. So the next thing we need to do is what? Take the derivative. So to do that, what should I do? Could do the quotient rule, or rewrite it and use the product rule, or rewrite it and do neither. f of x equals x to the fourth over x squared plus 1 over x squared, which is x squared plus x to the negative second. Yeah, recognize when you can use something simple. So if you use the quotient rule, it's no big deal. You probably wind up with the correct derivative anyway. But this makes things a little bit faster. F prime of x equals 2x minus 2x to the negative third. Right? Okay, calculus is over. Algebra time. Rewrite this. 2x minus 2 over x to the third. I don't want to lose any roots, meaning I don't want to just leave it like this and then wind up dividing both sides by x or something. That would lose a root for me. So I'm going to make a common denominator. Common denominator obviously is going to be x to the third. So that will turn that into 2x to the fourth minus 2 over x to the third. Do you agree? Okay. So I have a GCF here of 2. So I'm going to make this 2 times x to the fourth minus 1 over x to the third. So notice that with my derivative, I still have division by 0 when x is equal to 0. I don't have any other division by 0 introduced into this, so I don't have to worry about that. What I do need to do, though, is set this equal to 0, and then solve for x. So what should I do first? Multiply both sides by x cubed to get rid of the denominator, and then I can also divide both sides by 2 to get rid of that 2. And I'm left with x to the fourth minus 1 equals 0. Now what? No. You don't want to just add 1 to both sides and then take the square root of both sides and then take the fourth root of both sides. There are 4 possible roots here. If you took the fourth root, you might only get 2 of them. Yeah, factor it. This is a perfect square, this is a perfect square, and we're subtracting them. So this can factor into x squared plus 1 times x squared minus 1 equals 0. I can actually still factor this thing down and get x squared plus 1 times x plus 1 times x minus 1 equals 0. And yeah, you're right, you could have done zero product property there and then added 1 to both sides and that other one and gotten plus or minus 1. But this just factors it completely for me. Now I can zero product property this. X squared plus 1 equals 0. X plus 1 equals 0. X minus 1 equals 0. This one will be x equals negative 1. This will be x equals positive 1. I don't really need to write the plus. Then here we're going to subtract 1 from both sides. And we get x squared equals negative 1. And then square root both sides and you get the square root of negative 1, which is I. So you get x equals plus or minus I there, and then negative 1 and positive 1. So you actually found all 4 roots doing it this way, which is the preferred way. Obviously, we're not concerned about imaginary roots, so those 2 will disappear, and we're only going to have these 2. So my final critical numbers, if I was asked what the critical numbers were, would be x equals 0, x equals negative 1, x equals positive 1. Or I could write x equals plus or minus 1 and save myself a couple of strokes.
Lucky you. I don't know how.
Okay, so now what happens? Make your table. So set up the intervals, and we're going to use interval notation. So I'll start with negative infinity to negative 1, and then negative 1 to 0, and then 0 to 1, and then 1 to infinity. Got to pick some test numbers. Okay, negative 2 sounds good. Negative 1/2, painful but doable. Positive 1/2, 2. We don't need the magnitude, we just need the sign. So we take the negative 2 for this guy and plug it in. In the bottom, we get a positive number. So the denominator is positive. In the top, we get a positive result. So we are, very good. Take it and plug it into the derivative, not the original function. So we plug into the derivative, and in the denominator we actually get a negative, and in the numerator we get negative 2 to the 4th power is going to be big times another positive is big minus 2, still positive. Positive divided by negative is negative. All right? Negative 1/2 in the denominator is still negative. Negative 1/2 in the numerator becomes positive, but it's 1 over 2, 4, 8, 16. Or you could go 4 times 4 is 16. So you have 2 16ths, which is 1/8. 1/8 minus 2 is, so negative. Negative divided by negative is positive. Positive 1/2 now. The denominator this time is going to be positive, and the numerator will be negative. So our result will be negative. And then positive 2, denominator is positive, numerator is positive, so our result is positive. Okay, now remember what the graph was doing in the first place. Where did this critical number come from right here? That's a vertical asymptote. There is no maximum or minimum at a vertical asymptote. So for this critical number, we don't have a maximum or a minimum. It's a vertical asymptote. So we're going from decreasing to increasing here. That means it's doing that, which means we have a minimum here. And this is a vertical asymptote. I can actually label that if I want to. And then we are going from decreasing to increasing here. That looks like that. So this is a minimum as well. So find the relative extrema. We know they're both minima. Now we need to find the ordered pairs. We're going to have min, let me write relative min at, and I have 2 ordered pairs. Negative 1, comma something, positive 1, comma something. This time I do go into the original function. Negative 1 up here becomes positive 1 in the denominator. That is a 1 plus 1, which is 2, so negative 1 comma 2. And then the same analysis for that positive 1 gives me 2 as well. So I have 2 relative minima, and they occur at negative 1 comma 2 and positive 1 comma 2.